In section 6.4 and 6.5, our objective is to identify and use similar triangles and to use similarity theorems to prove triangles are similar. So remember when we started talking about similar polygons, what did we say is true about similar polygons? Angles, all of the angles have to be congruent. And what about the sides? They have to be proportional. So the angles have to be congruent and the sides have to be proportional. Those two things have to happen for figures to be similar. Well, what is the minimum amount of information that we really need? Let's look at some shortcuts. Let's look at these two triangles. Clearly different sizes, and I have some measuring devices here to prove that. Let's do some measuring starting with the angles. So let's see how these angles measure up. I put my protractor and I see that this first angle 60 to 70, it measures approximately 67 degrees, and I created this triangle to have the same angle measurements. Notice how this one, if I place this on the vertex, again we see 67 degrees. So I'm going to write down that we just noticed that these are both 67-degree angles. 67-degree angles. I'm going to go ahead and take, let me write that a little bit neater. I'm going to go ahead and take this protractor over to this other angle, and we'll notice that this angle measures approximately 32 degrees. And over here, again, this angle measures, let's fix that a little bit, 32 degrees similarly. So I made sure that 32 degrees, all three angles are congruent. Now you know we don't have to measure the third one. They have to add up to 180, so by the third angles theorem, yes, this one also has to be 81 degrees. So I made two triangles where the angles are congruent. That checks out in this picture. The angles are congruent. Clearly the sides are not of the same size. Let's check out what happens to the length of the side. So I've got my ruler here, and I'm going to start by measuring this side, and it looks like this longest side is approximately 114 units long. So the longest side of this triangle is 114 units long. That's the longest side. The longest side of the other triangle, definitely not the same size, looks to be about 81 units long. So the longest side over here, about 81 units long. Okay, let's measure the second longest side of each one now. Over here, we've got this side. And that side looks like it's about, I'm not right on the end there. Let's scoot over a bit. That looks like about 75 units long. So we'll record the second longest is about 75 units long, and then we'll go over to this second longest side on this one, and we see this one's about 105 units long. So second longest, 105. Let's go ahead and now measure the shortest side of both of these triangles. And it looks like this shortest side is about, well, let's try to be a little bit more precise here. That looks like it's about 60. And now we'll go measure this shortest side. How many units is that? About, it looks like 43. We're measuring 43 units long. So 43 for the shortest side here. Well, what did we say about the similar figures? Yes, the angles have to be congruent and the sides have to be proportional. Well, I made the two triangles have angles that are congruent. What do we see about the sides? Well, let's set up ratios. That's what proportional means. The ratios are equal. So I'm going to take longest side, and I'm going to make ratios out of them. 114 over 81. We'll take out our calculator. So we're going to simplify this ratio in the calculator. 114 divided by 81 equals, so about 1.4 is what we'll write down. That's approximately 1.4. Okay, let's take the two medium size now, the 105 divided by the 75. And while we're at it, since we're calculating, let's go ahead and write down the short sides too. So we'll figure out what this one equals, and 60 divided by 43, those short sides, those corresponding parts. Let's see what they simplify to. 105 divided by 75. Oops, let's try that again. Clear it all up. 105 divided by, let's try this again. 105 divided by 75, 1.4. And finally, 60 divided by 43, those corresponding shortest sides, also about 1.4. So you see, we made the angles congruent, and the product of that was the sides had to be proportional. So the point here is, do we have to check for everything, or is it going to happen? And the answer is, if I make the angles congruent, I see the sides will be proportional. So there's our first shortcut, is the angle-angle similarity postulate. If two angles of one triangle are congruent to two angles of another triangle, those two triangles must be similar. So let's first write that this is for angle-angle similarity postulate. And let's make a picture, because that says a lot about what we're looking at. One pair of angles congruent, a second pair of angles congruent. As you saw from our little exploration, we don't need to know more than that. We measured these two angles, we saw those are congruent, and those third angles had to be congruent. So we saw this angle congruent to this angle, second angle congruent to second angle, and therefore we've got the similar triangle. So let's go ahead and write down what this similarity postulate tells us. If two angles of a triangle are congruent to two angles of another triangle, then the triangles are similar. Remember, you can pause or rewind the video at any time to get a better look for what we've done. Let's do some examples. Using the angle-angle similarity postulate, show whether the two triangles are similar. If they are similar, write a similarity statement. So it says to use angle-angle similarity postulate to show whether, so that means it's a yes or no question, the two triangles are similar. So they may or may not be. If they are, we'll write a similarity statement. So I see in this picture, I've got two angles that do not look the same measures as these two angles. I have an 85 degrees and an 85 degrees, but I have angles that are missing in measure. So let's figure out what those third angles measure. 85 plus 45, that makes 130, and we know that all the angles have to add up to 180, so subtract 130 and we get 50. So this missing angle measures 50 degrees. I don't have to find this one because I see that this 50 degrees is the same as 50 degrees that's here, and I have two angles congruent to two angles. Therefore, the answer to this, yes, these are similar. Therefore, the similarity statement can be written, and we start with triangle, JKL, always the one that comes first or to the left or on top, similar to triangle. Now let's match up properly here. J corresponds with the 45-degree angle in here, which is the y. So y goes first. K I wrote second. K says 50, so that goes with the one that's 50, and that's z. And then the third angle after z is x. So there's my similarity statement to go along with saying that they're similar. In this one, it's a little bit trickier to see because the triangles are overlapping each other. So here's what I like to do is draw the two triangles separately. I've got this little triangle that's P, T, and Q with a 50 degrees and a 45 degrees. Then we've got the larger triangle that goes from P to R to S. So let's try to draw that one as we see it, P, R, and S, and there's an 85 degrees in R, and the P is 50 degrees, so we can put that there. So let's look at the angle measures that we have. Again, I see a congruent pair of angles, 50 degrees and 50 degrees. The third angle, or the second angle, 45 degrees, doesn't match this second angle, 85 degrees, so I need to find a missing angle measure. Let's maybe find it in the big one. 50 plus 85, that's 135. Subtract from 180, 135, and we get 45. So angle S is 45 degrees. So it does look like we have two pairs of congruent angles. Therefore, again, these are similar. And we can write the similarity statement. Why don't you pause the video and try to do that on your own? So did you get PQT is similar to P is the 50, so P is the 50. Q is the 45 and S is the 45 and T is the third one to go with R. Yay. Let's practice writing a proof. Writing a proof to show that these two triangles are similar. You know what? We can practice this in class. Let's move on. Maybe you try it and see how we do in class. In addition to angles being congruent, we remember that the sides have to be proportional. So our other shortcut is the side, side, side similarity theorem, saying that as long as the corresponding sides are proportional, the triangles will be similar. So again, this says to us if the corresponding sides of two triangles are similar, or if the corresponding sides of two triangles are proportional, remember we want sides to be proportional, then the triangles are similar. So giving you a picture, make the two triangles not look the same size, but make them look similar. Perhaps I give this a length of 10 units, 12 units, and 8 units. If these are similar, we could say with a scale factor of 2 to 1, meaning this one is half as big as this one, or this one is twice as big as this one. These sides would be 5, 6, and 4, right? Half as big as those. 10 divided by 2, 12 divided by 2, 8 divided by 2. So this shows that the sides are proportional, and that's all we would need to know. Let's look at a couple of examples that demonstrate the side-side-side similarity theorem. First one, it says verify that the triangle ABC is similar to triangle DEF. Find the scale factor of triangle ABC to triangle DEF. Verify. That's a very important word there. That means we know they are similar, so this is just show it. Just show it. We know they are. It's not a yes or no question. So to show it, and knowing I have the sides and only the sides, I am trying to check that the sides are proportional. So I am using the side similarity theorem. I'm checking that the sides are proportional. Well, how do I know which ones correspond? I can use this statement, or because I have all three sides, I can match small number with small number. Start there. 18 divided by 24. We will simplify that fraction, 3/4. Then I'll do medium number. Let's see, medium number. Next biggest is 21. Next biggest here is 28. So 21 over 28. That also simplifies to 3/4. Finally, the largest ones, 33 and 44, 33 over 44, that also simplifies to 3/4. So we're showing that the sides are proportional using SSS. So there we have verified it using side, the sides are proportional, and the scale factor is found. So the scale factor is 3/4. So I verified it here, and I found the scale factor here. Want to try the next one on your own? See how you do? Come back. So if you tried the next one, you verified it by showing that the large side over the large side is 3/2. The medium side over the medium side is 3/2. The small side over the small side is 3/2. This proves the sides are proportional by SSS. This is SSS showing. And our scale factor, 3/2. We always go left to right, giving our scale factor. Here's another type of problem that we'll see. Determine which two of the three triangles are similar. Find the scale factor for the pair. So we're trying to determine which of these two are similar. It's going to be a guess and check unless you have an idea right off the bat and you make a very good educated guess. Let's start by checking if the first two are similar. So again, we're going to take large number over large number. Those are the corresponding lengths. 24 over 18 and see what that simplifies into. 24 divides by 6, 18 divides by 6. Okay, let's do now the medium side is 20 over the medium side is 16. So 20 over 16, that simplifies into divide by 4, not the same fraction. So we see that those are not similar because the sides are not proportional. Let's try another pair. How about we try the first triangle with the third triangle, see how those work. So again, large side over large side. So we'll do now 24 over 30. That simplifies into 4/5. Medium side is 20, medium size is 25. 20 over 25, again 4/5. We have to check the last because all the sides have to be proportional, and 16/20 also simplifies into 4/5. So this shows us that it is the first and the third triangles that are proportional, or that are similar because the sides are proportional. So we will write which two those are. Triangle ABC is similar to triangle. So we went over the largest side and then over the smallest side to make our statement. So again, we'll do that. Largest side is 30, smallest side is 20. So GHJ. The scale factor is what we got when we saw that the sides are proportional, 4/5. Our last shortcut is a combination of the two, the side angle side similarity theorem. SAS for side angle side similarity theorem. That's a combination of the two. So in our picture, what we want to show is two pairs of sides that are proportional. So two pairs of sides that are proportional. So I'm going to make maybe these 8 and 10, and these will be 4 and 5. So we see that this triangle is twice as long in the lengths that this triangle is. And then the angle that's between the two sides, so this side and this side, if I trace them where they connect is up here, this angle is congruent to the included angle in this triangle. That's this one. Tracing those two sides that are marked, the included angle is that one. So that's something like what our picture would look. So if we have two pairs of corresponding sides that are proportional and the included angles are congruent, then the triangles are similar. Okay, so a combination of those last two shortcuts. Let's take a look at these examples. Is there enough information to determine whether these triangles are similar? Is there enough information? So that's a yes or no question. If so, if yes, write a similarity statement and find the scale factor. Let's look at the first one. I do see a pair of congruent angles. That's promising. I don't see a second pair, so I'm not using angle. I do see two sides that have numbers on them, but If I trace those two sides, where they connect is at this angle right here, and that is not the angle for which I have a measure. So this is not side angle side, where the angle is included. This is side side angle, side, and an angle after it. I didn't even check yet if the sides are proportional, but it doesn't matter because side, and angle is not one of our shortcuts. So is there enough information? No, there is not enough information for this one. Second picture, it's kind of hard to tell that we have two triangles. So maybe I draw them separately. This little guy right here, I'm going to draw him away from the picture where I mark everything as marked in the picture, CDG, where CD is 15 and CG is 20. And then we've got the larger of the two triangles. Draw that one as well. This is C, E, and F. And this length all together is 27 if I add those. And this length all together, 20 and 16 put together, is 36. So 36 here if I add those. How about any angles? Well, there's no angle measures, but remember these two triangles were inside each other and both used angle C. So by the reflexive property, angle C is congruent to himself. Remember, angle C congruent to angle C, we see the same thing on both sides. That's the reflexive property. We'll keep that in mind for when we do some more proofs. So angle C congruent to angle C. I see that that's the included angle because this side connects this side at that angle. This side connects this side at that angle. So we have a pair of congruent angles. Let's see if the surrounding sides are proportional. So I'm going to do 15, the little side, over the little side 27, and we'll reduce that. That reduces to 5/9. And then the large side, 20 over 36, that also reduces to 5/9. So yes, by side angle side, there is enough information to say that triangle, we'll do the first CDG, is similar to triangle. So C corresponds with C, CD is the small side, and CE is the small side, and then F. And the scale factor we found to be 5/9. So by side angle side, we proved the triangles are similar, and the scale factor is 5/9 that we saw by the proportional sides. Now you have it. So remember our three similarity theorems. AAA is a similarity postulate, angle, or all the sides are proportional and we don't know anything about the angles, or a combination of the two sides and the included angle. Can you write a short summary?